So welcome everyone, welcome to the second of the PSA's Political Psychology Group's autumn term research seminars. And we're delighted to have this week, we're genuinely international, delighted to welcome Klara Muller from the University of Mannheim. And as you can see, Klara's got a fascinating paper that's looking at, or project that's looking at whether events change minds or samples. So I'm going to let Klara introduce her paper, and we'll have about half an hour for her to present, and then we'll have about half an hour of discussions. So Klara, very warm welcome, and look forward very much to hearing what you have to say.
Yeah, thanks so much, Ben, and thanks so much for having me. I'm really looking forward to presenting some research here, and I'm happy to see so many of you to join for some kind of scientific lunch break. So I hope I can provide some good entertainment in this break. I'm Klara. I'm a researcher based at the University of Mannheim in Germany, and my research largely focuses on political behavior, public opinion, and I set a specific focus on measurement questions, measurement bias. So I kind of bring a, let's say, survey methodological perspective into public opinion research. And what I'm presenting today is some ongoing work that I entitled Do Events Change Minds or Samples?, where I aim to develop a framework to identify biases in causal inference that focuses on the effects of events, and bias that is rooted in sample compositions that may be distorted after certain events. Now, this whole research is motivated.
Klara, you've muted yourself.
Okay, now it should work.
That's fine.
Perfect. Okay, so what motivated this research is that empirical social science heavily relies on survey data. And we also know that survey data is flawed and imperfectly reflects citizens' true preferences. For instance, because not everybody wants to participate in a survey, or if people do so, they might not respond truthfully. And that is, surveys are not collected within a vacuum, but rather in a political context where respondents are continuously exposed to different influences that might affect if and how they respond. And from political behavior, we know that such changes in people's political context can actually affect their preferences, attitudes, and behaviors. And from survey research, on the other hand, we know that changes, rather in people's narrower personal context, could also alter their survey response behavior. And what I do in this research, I kind of bridge those two strands of literature, and I question how not only personal events, but rather larger political events also affect survey response and participation behavior, and how this then might affect the accuracy of public opinion measurements if, in response to certain events, some people are very responsive or less responsive, and thus over or underrepresented in survey samples. Now, in studying how political events affect certain attitudes of any kind of political behavior, one increasingly prominent approach, especially in the past years, has been the unexpected event during survey design. And this approach leverages the, as the name says, unexpected occurrence of an event during the survey field time. And the event is then treated as a kind of natural experiment where pre-event participants resemble the control group and post-event participants are the treatment group. And for causal identification, this approach relies on several assumptions. One of them is the excludability assumption. That means we should make sure that there are no collateral events that could affect the outcome variable, and also that there are no time trends in the outcome variable. And another assumption for causal identification is that of ignorability. And that basically says that it should be reasonable to assume that survey participation and the timing of survey participation is random. So the assignment into treatment and control group should be random. And this is precisely the assumption where my study departs from and that I question. Because we know from existing research that survey participation and its timing is far from random. And even in single cross-sectional survey waves, there are certain characteristics that make people more likely to, say, respond later towards the end of the survey field time or earlier, and those people differ. And what I additionally question is whether the event itself that is studied with this design could also actually violate the ignorability assumption and making people more or less likely to participate after the event. Now, to show you the framework that I developed to potentially understand how the ignorability assumption could be violated, let's have a very quick detour into the formalization and how causal identification actually works with this approach. So ideally, to identify causal effects, we can observe the same individual before an event and after an event to then compare the outcome variables and identify this within-person causal effect, which is the beauty of panel data, that we could actually do this. However, here we are not dealing with panel data, but with one survey wave, usually cross-sectional survey waves. And that means that each individual is either observed before the event or after the event, but never at both points in time. So what we have to do to identify causal effects is to calculate the average treatment effect, and that is simply comparing the difference in means for a certain outcome between a post-event and pre-event sample. Now, for unbiased causal identification, ideally, these two samples should be should have the exact same sample composition. However, this is rarely the case, and specifically if I suspect that the event affects the sample composition. If that is the case and the sample composition between pre and post-event differ, the causal effect that we estimate actually captures the true causal effect, but also something which I call the compositional effect or compositional bias that precisely arises because the post-event sample differs from the pre-event sample. Now, if we zoom in into precisely this compositional bias, this is composed or basically resembles the difference between a treatment group sample that is actually exposed to the event of the effect to the effect of the event. So the sample, how it would look like if only those who respond after the event are actually in the sample. And then another sample that would be the treatment group in a counterfactual world where the event did not happen. So this is hypothetical. And of course, the differences between these two treatment group samples could be regarding observable factors, like, for instance, sociodemographics, but it could also be rooted in unobservable factors or unobserved factors. And to understand how compositional bias rooted in observable and unobservable factors might bias our estimates that we obtain with this unexpected events design, I propose 5 steps. And the majority of those steps actually rely on best practices that are actually already established for the unexpected events design. The first one is to just estimate your baseline models. That is, find an appropriate model specification that fits your outcome variable, find a good and reasonable covariate selection, maybe use fixed effects, because something, for instance, a very popular data set for the unexpected events design is the European Social Survey that employs multi-stage sampling, where people in one region are interviewed before people in another region. So just the place of residence already affects your timing of survey participation, so it might make sense to include region-level fixed effects, for instance. So the first step, find a good baseline model, estimate it, and identify your first, hopefully, causal effect. To test the robustness of this effect, you can then reduce the bandwidth of days or time around the event to see whether your effect is driven by differences between very early and very late respondents. And to specify a good bandwidth, I propose to conduct power analysis to kind of find a good balance between narrowing the bandwidth as much as possible while still maintaining sufficient statistical power. Now, across the different bandwidths that seem to be reasonable for the case under study, you can then have a descriptive look at the differences between the treatment and control group to understand how the composition of samples differs. And this step then informs a 4th step, which is entropy balancing. I will say a bit more about that in a minute. And that is a way to control for the compositional differences based on these observable factors that you have identified in step 3. And based on those balanced samples, then you should just re-estimate the models that you have estimated in step 1. And all those 4 steps are there to have a good baseline and at best already mitigate any compositional bias that is rooted in observable factors. Now, what about the unobservable factors? Here I suggest to conduct another step, which is sensitivity analysis. And this is itself is an established procedure, but it's new to incorporate it in the unexpected events design. And that's a way to identify how strong an unobserved confounder potentially would need to be to bias the estimated effect. So while by design, it's not really possible to quantify and completely, let's say, remove any bias that is rooted in unobservables, it's at least helpful for your validity of the causal inference to gain an understanding of how likely it is that your results might be biased. So the aim here is to identify the potential of bias that is rooted in unobservable factors. Now, let's apply those 5 steps. And to apply that, I have one running example, and that is the Charlie Hebdo terror attacks in Paris, 2015. I'm pretty sure people know this event, where coincidentally, the field time of one European social survey wave happened, which gives us a sample of sufficient size and also a sufficiently large control and treatment group divided by the terror events. And the benefit of studying terror attacks to show you the application of this framework is that terror events are truly unexpected. So it allows me to keep constant any other sources of bias, for instance, that might be rooted in people anticipating the event and even before the event already adapting their attitudes or survey behavior. And as an outcome variable that I'm studying here, I'm choosing satisfaction with government as it represents a typical rally around the flag effect. It's really well studied for that case. And it's just a nice application to test, let's say, a hard case or some effect that is very well established in the literature and take a closer look how likely it is that such established findings might be prone to bias. Now, as a first step, I estimate a baseline model. You see here 2 models. One is the naive model, just including the treatment indicator as explanatory variable. And the other one additionally includes an indicator of time to kind of gain an understanding how immediately the effect was present or whether it kind of developed incrementally. And both models include region-level fixed effects for set reasons of the structure of the ESS sampling procedure. Now, you see in both cases that there was a significant increase in satisfaction with government after the terror attack. So this is a textbook example of a rally round the flag effect with just this baseline model. Now, to gain an understanding of its robustness and potential bias, I conduct power analysis to select reasonable bandwidth. You see here the different lines are there for identifying different effect sizes. And you can see that even for small effect sizes, as soon as we have a sample of, let's say, or bandwidth of around plus minus 25 days around the event, we're statistically well powered to identify even small effects. And then on the lower end, we should maybe stop at a bandwidth of 8 days around the event to identify relatively large effects. So this gives me a frame between which I can reduce the bandwidth. Now, continuing with the third step of having a descriptive assessment, you see here those different bandwidths and a selection of covariates, mostly sociodemographics and time invariant covariates, to assess how those pre and post-event samples differ. Now, I would say a textbook case would be that with decreasing bandwidth, so narrower bandwidth, the differences should become smaller and smaller, which you kind of see here, although it's mostly the uncertainty around those differences that increases. However, it already gives us a kind of an understanding that there are some differences, but also at the same time, it doesn't give us an alarming picture. Now, based on this, I conduct entropy balancing. And that's a procedure to reweigh the control group observations in a way to match the covariate distribution of the treatment group. which then doesn't give us the average treatment effect, but the average treatment effect among the treated. And usually you pick social demographic variables where you have reasons to assume that they influence both the outcome variable of interest, so satisfaction with government, and potentially also survey response behavior. And yeah, one suggestion is to actually focus on time invariant covariates to avoid any post-treatment bias and avoid balancing on covariates that might be affected by the event. Now, based on this entropy balancing, I re-estimate the models for, again, a selection of different bandwidths. And you might notice that now the narrowest bandwidth is 16 days and not 8 days as obtained from the power analysis. And that sometimes the entropy balancing is the restricting factor because the balancing model just stops converging with too narrow bandwidths because some variables might become collinear. So you pick the narrowest possible bandwidth either through the power analysis or the entropy balancing. Nevertheless, in any of those cases, you see that if we control for observable compositional differences, the effect remains substantively unchanged. There are small differences, but in all cases, do we have a positive and significant effect of the terror attack on satisfaction with government. So it doesn't look like the Rayleigh effect is just an artifact if we control for observable compositional differences. Now, what about the unobservables? The sensitivity analysis that I propose, again, is composed of different steps. And one is calculating the so-called robustness value. This is a value that quantifies how strong an unobserved confounder would need to be, potentially, to meaningfully change the estimated effect. And this value resembles the minimum proportion of variance that an omitted or unobservable, which is basically the same, variable must explain, both in the outcome variable of interest, but also in the survey or here entropy weights. So it could be that an outcome that an unobserved confounder has a large effect on the outcome variable. However, the both samples are super similar in this variable. At the same time, it could be that the post-event sample people are very low in this variable, but then it's very represented in the post-event sample. So whenever an unobserved confounder has such effects, there's the potential for bias. And the robustness value indicates, as said, the minimum proportion of variance that an omitted variable must explain to reach a chosen bias threshold. And that's something that needs to be specified. What I do here in this example is I specify the threshold as completely reducing the estimate to 0, which is certainly a conservative approach. You could also say, okay, you set the threshold to halving the causal estimate, or depending on the case, say, for instance, you have a race between two candidates, then of course you might choose the threshold as flipping around the 0.5 mark, or kind of being a threshold where the outcome would flip from one outcome to the other. So this is case specific. And a robustness value close to 1 indicates that a huge portion of variance would need to be explained by an omitted variable. So only implausibly strong confounders could bias the results. Hence, you have a very robust effect. On the other hand, a robustness value closer to 0 indicates that already weak confounders could overturn your results and you have a very sensitive effect. Now, looking at this for the Charlie Hebdo example, you see here on the x-axis different biases as proportion of the estimate. So basically different bias thresholds. From halving the effect, you see the one vertical line, to completely reducing it to 0. And then on the y-axis, the respective robustness value for all four bandwidths in the different colors. And you can see that, of course, the robustness value is higher, so more variance needs to be explained to completely reduce the estimate to 0. And also effects are a little bit more sensitive for the more narrow bandwidth, which makes sense because also the sample size is smaller. Now, while this at first sight doesn't look alarming, we still don't know how this relates to actually the influence that observed covariates have on the outcome variable and the survey weights. And also, this value assumes that the influence of an unobserved confounder is equally strong on the outcome variable and the survey weights. However, it could be that it has different large effects on both of these measures. And to acknowledge that and also put this the strength of an unobserved confounder into context of observed variables, we can take a look at contour plots. Now, here on the x-axis, which is called the alignment, you can see the explained variation in the outcome variable, while the y-axis represents the explained variation in the entropy weights. And then you see where actual observed variables are located in this plot. And then on the top right corner, the blue shaded area, which is called the killer confounder zone, which I find slightly unethical in the context of terror events. But let's stick with it for now. It's the area where an unobserved confounder would need to be located to substantively bias your results by the chosen threshold. So in this case, to bias the result or the estimate to 0. And for this full sample, we see that it seems quite unlikely. This is quite far away from the influence of observed variables. And it slightly changes if we take a look at the more narrow bandwidths. You can see here for 20 days, and for 16 days, it comes even closer to the influence of observed variables. However, in all cases, this kind of draws a picture of the rally around the flag effect after this specific case of the Charlie Hebdo attacks to be quite robust. Now, to understand how this instrument performs for other cases and other data sets and also with other outcome variables, what I do is I extend the application. And I extend it to existing studies that employ the unexpected events during survey design. Also focus on terror attacks for said reason that this is a very clear-cut event and keeps other biases constant. And again, on rally-style outcomes to continue testing this well-established phenomenon and assessing its potential for bias. Further, another selection criterion is that the papers I replicate should be published after 2020, because that is when the, let's say, currently most prominent best practices for this design have been established, so I can actually run through those best practices. And this left me with 4 papers that I'm replicating, focusing on different cases of terror attacks, slightly different outcome variables. We have trust in politician, satisfaction with government, prime minister approval or trust in politics, and also an extension beyond the European social survey data with an addition of BES data and Afrobarometer. And because some cases overlap, this leaves me with 14 cases in total, covering 4 different outcome variables and 3 different data sources. Now, what I do in a slightly more condensed manner is I estimate the baseline models for each case. I narrow down the bandwidth. So you see here the full sample on the left side, and then the case-specific narrowest bandwidth on the right side, and then employ entropy balancing. And for almost all cases, I simply adopt the model specification that has been established in the original paper. Some have fixed effects, some don't, some include more covariates, some include less. But in all those cases, you see that usually controlling for observed compositional differences by entropy balancing doesn't significantly change the results. There's this one case with Tel Aviv in 2003, where on the lower end, on the left-hand side, where for some reason entropy balancing makes the effect significantly negative, but this is certainly an outlier. In the other cases, the substantive implication of the result remains unchanged. Now, what about the unobservable confounders or unobserved confounders? To make it slightly easier than having a contour plot for all those cases, I introduce an additional measure that kind of condenses the information of the contour plot into one number. And that is the so-called minimum relative confounding strength. And that is a value that assesses how strong an unobserved confounder must be relative to observed covariates to bias the estimated effect. And I slightly tweak this, departing from existing literature on it, and define the so-called MRCS max, which is the absolute value of this quantity. of the most influential observed covariate that is included in the model. And this is then interpreted in a way that an MRCS max larger than 1 indicates that an unobserved confounder must be more influential than this observed benchmark. And a value below 1 indicates that bias would already occur if the unobserved confounder is less influential than this benchmark. Now, taking a look at this quantity for those different cases, you see here also the robustness value. But for now, let's focus on those 2 middle columns with the MRCS max. Highlighting a few examples that stand out. First of all, Manchester Ariana Grande concert in 2017 seems to be a very robust case, also because it's a huge sample. So just for statistical and technical reasons, it's already difficult to have huge bias in these results or have insignificant results. And you see, like, an unobserved confounder would need to be around 300 times as influential as the respective most influential observed variable. So this is a pretty robust effect. Then picking up again, Paris 2015, you see here also this information supports what we saw in the more thorough example beforehand. This effect seems to be quite robust. Like, an unobserved confounder would need to be multiple times more influential than very influential observed variables. And then another example that is certainly more sensitive is the Berlin example, the attack at the Christmas market in 2016. Here you see that in one case, it would already be sufficient if an unobserved confounder would explain half the variance as compared to a very influential observed variable to bias the result. Now, zooming out again to understand what we can learn from this framework, there are actually 2 dimensions of takeaways. The first one is methodologically, and I assume that events may also affect survey response and not just political outcome variables. And there are certainly ways to effectively mitigate compositional bias that is rooted in observable factors. Additionally, while by design, we cannot completely rule out bias based on unobserved factors, there are certainly ways to gauge its potential impact. And I propose that such kind of sensitivity analysis should routinely be incorporated into event-focused studies and kind of this best practice flow of the unexpected events design to, first of all, thoroughly test the ignorability assumption and, in general, improve the validity of causal inference. And note here that certainly very case-specific choices should be made for the exact specification of this 5-step framework. So I have here kind of presented a more generalized specification, but you should, for instance, make very sensible selections of balancing covariates, choosing a case-appropriate bias threshold, and then also pick benchmark variables that might be more expressive than just picking the strongest observed confounder. Now, turning to the substantive takeaways, having assessed the specific case of rally-around-the-flag effects, there seems to be some variation across the cases in how likely it is that there is compositional bias. However, overall, these established phenomena of rally-around-the-flag effect seem to be quite robust against unobserved confounding. And then something has been emphasized that was already established in the literature, and that is that specifically the Paris attacks of 2015 are a very strong textbook example of rally-around-the-flag effects in Europe. And with that, I first of all thank you for spending your time here in your lunch break. I'm really looking forward to your questions and a fruitful discussion. And also, I want to take the opportunity of having you here to say that I'm currently finishing up my PhD. I'm in the final phase of my PhD research, and I'm certainly on the hunt for postdoc positions. So if you happen to know of any open positions where you, now that you have seen some snippets of my research, think it could be a good fit or it could be interesting, please let me know. Feel free to reach out. And of course, also outside of any postdoc related questions, feel free to reach out. I'm always happy to talk about research, talk about collaborations, and hear about your research. Yes, thank you very much.